Welcome to the final L3 applications presentation for Group 9. In our initial design, we proposed to build a rear-wheel drive glider that was elevated to give the wing a 5-degree angle of attack. The inverse Zimmermann was chosen as the plan form of our wing, while a cambered wing was shown to form better. Using a flat plate would be more straightforward and lighter, allowing us to focus on building a sturdier undercarriage. Use of Tornado and MATLAB produced a predicted glide distance of 1.9 meters. The initial prototype was then fabricated and made ready for testing. During the first test, conducted at a height of 0.7 meters, it can be seen that our model faced several issues. The gears connecting the motor and wheel axle would unmesh before the model reached the end of the ramp, resulting in a severe loss in velocity. One positive takeaway, though, was that our model travelled in a straight line. Due to the presence of a tailplane, the positioning of the undercarriage with respect to the wing's aerodynamic centre was restricted, resulting in an undesired pitch-up behaviour. With these results and problems identified, the next phase was to improve on our existing model. In this improved design, the tail of our structure was removed, saving weight and eliminating the chance of tail strike. This also allowed us greater flexibility in the positioning of the undercarriage relative to the wing. Another key improvement we made was to use wider gears, making gear interaction easier and therefore solving the unmeshing issue. Rather than using an interference fit for the motor, we decided to install a motor bracket, thus improving the motor-axle connection. The second fabrication process was much easier this time, as many of the steps were similar to the first iteration. A larger wing was manufactured to give us more lift. This was possible only because of the weight reduction that came with having a shorter undercarriage. In our first trial, the robot was able to glide about 1 meter off of a 0.7 meter high table, a significant improvement from our first model. During the actual test, the furthest flight distance travelled by the glider was 1.6 meters. This is less than the model predictions, which assumed a higher ramp velocity. However, using the actual ramp velocity of 1.3 meters per second in the model, it can be seen that the glider performed better due to incorrectly modelled pitching moments or ground effect. In one of the tests, the glider's slight CG bias to its port side was evident as it would veer to the left during flight. This could be solved by designing a cage for electrical components to sit in, thus centralising weight components. This would also involve a reorganisation of our circuitry into a more compact form. Our model would also pitch up at the start of the ramp phase. This was an unforeseen problem that occurred due to the motor code's rapid delivery of torque, as no wheel slip was expected. By implementing a more gradual increase, this problem would be alleviated. The alternatives would be to change the chassis to a front-wheel drive system or to extend the wheelbase of our structure. All in all, it was a fulfilling project that was also our first foray into actual construction of a mechanical structure. Besides the improvements already highlighted, our main takeaway was that our primary focus during the design phase should have been on the structural stiffness and stability of moving parts. The majority of problems in the days leading up to the actual test were caused by issues with the undercarriage. However, with this experience, we are confident of designing and building a better mechanical structure in the future. We hope you've enjoyed our presentation.